Welcome to Unite Now, where we bring unity to you, wherever you are.
Hello everyone, and welcome to Unite Now, and more specifically to this presentation on adaptive performance. Today I'm going to tell you a little bit about how to use adaptive performance. I'm going to tell you a little bit about what it does, and I'm going to tell you a little bit about how to use it to increase the performance and optimize your mobile applications, particularly those with very heavy graphics workloads or that do a series of very heavy graphics operations over a long period of time, such as the AAA mobile titles we see on the market today. In order to allow you to put a face and name to the voice you're hearing, that face on screen is me. My name is Benjamin Mitchell. I work as an engineer in the Galaxy GameDev team at Samsung Electronics. So in this short presentation, I'm going to cover a few things. Firstly, I'm going to do a few introductory topics on the GameDev team. I'm going to tell you who we are and what we do. And I'm going to tell you about the GameSDK, which contains all of the technology that allows us to actually work. It actually is behind all these tools. Then I'll describe the Unity Adaptive Performance package before going a bit more in depth on how to use it, how to use adaptive performance, and I'll give you some examples of how we used it in Call of Duty Mobile. And then I'll finish up with some discussion of the impressive features coming up in the next release and supplement those with some examples as well. So I'll start off with Galaxy GameDev. Some of you may already know what we do, others may not have heard of us. Galaxy GameDev is a team that works within Samsung. We primarily work with mobile game developers to optimize their games on mobile platforms, kind of our main focus, to make mobile games as desktop ready, as console ready as possible, and as accessible as possible. We work all over the world, and therefore we have to have Samsung Galaxy GameDev teams located all over the world. We currently have research institutes in the United States, in the United Kingdom, in Ukraine, China, and South Korea. In total, we're a team of about 30 engineers from 5 different countries, all working together. So I couldn't introduce us without showing you our handsome faces. So this is us. As I said before, there's about 30 people in 5 countries working together, but we tend to collaborate quite a lot on projects. Our main focus is something we call camps, which is essentially when we travel, a group of us travel from different research institutes, meet in one of the countries, and go to a game developer's office and work on their game engine specifically to really hyper-optimize the performance for that game. And generally we collaborate on those for a series of weeks or months or however long it takes. We have a fairly extensive list of partners, so we're working with various game engine companies and game companies all the time. In addition to the companies listed here, we work with various game studios and collaborate with a bunch of game companies that use in-house engines. We work with all sizes of game companies, so we work from the biggest partners, biggest game engine companies, right down to the small indie teams. In terms of what we actually do, in short, the first step is game engine optimization, which is kind of the most important part. So for larger projects, this means we get hands-on with the engine source and we tweak it for the project specifically, make sure the render passes are exactly what they want, make sure the layout is exactly how we need it. And then for smaller projects, we focus on a bit more widespread optimization. So this is usually like performance suggestions, graphics suggestions, any kind of optimization suggestion we can give to the developers to use either on their assets or on the engine they're using. For many developers, they're going to see the performance benefits of our changes without ever actually interacting with us, since through our collaborations with the big engine game companies such as Unity, we can optimize the game itself, the engine itself, and then game developers can see the better performance by default when just using the game engine. We then support the developer with something called device loaners. So these are basically, we can give newer devices or even unreleased devices to developers to work on specific project titles. If you just sign an NDA with us in advance, we can then support you to share these devices directly to you, and you can get them before launch. So for example, if you were a game company that's already collaborating with us, you could have received a Galaxy Fold prior to the launch of the Galaxy Fold to test your application on. We also provide released phones as samples for testing. As the third prong of our support, we provide a deep workload analysis through detailed profiling of your game. This is primarily focused on the graphical aspects of the game, especially focusing on API usage. This information is going to help you choose the appropriate graphic quality options or modify source for the best performance. And finally, we share the analysis tools we use and teach developers how best to use them. So our primary purpose here is to improve the state of the mobile gaming industry. We want to make games just better for everyone on mobile. So teaching developers how best to make these games on mobile optimally as possible is as much a part of this as improving game performance ourselves is. So that's a quick introduction to us to allow you to know who we are. And now I'm going to talk about the Galaxy Game SDK. Adaptive performance is developed out of the Galaxy Game SDK, so it uses the functionality of the Game SDK to do exactly what it does. The GameSDK is host to a collection of powerful technologies for game development and mobile optimization, particularly hardware level optimization. But before I go into any further detail, I'm going to show you a quick video that shows the power of the GameSDK and what it can actually do. So this video is the result of performance comparison when the same APK, in this case the Megacity demo that Unity created, is installed on the same device. So no source code or assets have changed, nor has the hardware it's running on. Yet we can still see a very clear difference in frames per second. If you look at the left side, there's some yellow text at the top of each of the videos. The left side is running at about 26 FPS, while the right side is running at about 20 FPS. And as I'm sure you've guessed, this difference was entirely thanks to the GameSDK. So what did it do? Before I go in depth on what GameSDK did specifically, I think I need to outline some of the restraints of mobile that created the need for the GameSDK in the first place. So firstly, mobile phones don't have any active cooling systems like desktop machines and consoles do. So they don't have a fan, they don't have any water cooling, that sort of thing. Therefore, on mobile, heat is regulated to prevent high temperature. That is, thermal throttling is what we call it, works by itself on the device to control the temperature. It essentially slows your phone down by reducing the CPU and GPU frequencies to make it not consume as much heat. So when playing a high-spec game, a high CPU and GPU frequency is required to run the game at the expected graphics level. However, the higher the core frequencies, the higher the heat generation. Therefore, on mobile, when the device reaches this certain temperature, after a while of running at a high CPU and GPU frequency, it's going to start to thermal throttle, it's going to start to lower the GPU frequencies, lower the CPU frequencies in order to maintain the cooler heat. So the graph on the right shows a before and after of heat control. If you look at the graph, the CPU frequency stays fairly high immediately, and then as soon as the heat is generated to a certain point, we start to experience throttling. The CPU frequency starts to drop fairly fast, and then at the same time, as a result, the frame per second also falls very sharply. Second part of the limitations of mobile is mobile phones use limited batteries. So therefore, wherever possible, it is necessary to use the lower core frequency to minimize the current costs while still maintaining performance. So always the lower frequency should be used in order to save power, essentially. Saving battery and reducing thermal costs are the core problems here. So these are the limitations of mobile platforms, but in fact, the biggest limitation here is that the developer can't actually control when thermal throttling takes place, or even really know when it's going to take place. The temperature information of the device, the CPU and GPU frequencies themselves, they're all out of control for the developer. In other words, these restrictions are always happening as part of the game developer's game, but it's something they just don't have any control over whatsoever. So in order to solve and support these problems, we created the Galaxy Game SDK. Galaxy Game SDK was first announced at GDC in 2019, and through the Game SDK, power and temperature of the device, as well as some general hint information of various device statistics, can be communicated directly with the game application. Therefore, by using the Game SDK, game developers can use a variety of information from the device in real time, and it makes them able to actually react to it and optimize the application for it. Galaxy Game SDK currently supports the Galaxy S10, Note 10, Galaxy Fold and Galaxy Tab S6, as well as anything newer such as the Galaxy S20, and support for many other Galaxy devices is in the process of being added. Game SDK can be used by individual game developers, but we want many game developers using the game engine to be able to use the Game SDK more conveniently. Therefore, we developed adaptive performance in collaboration with Unity. So I'll explain a little bit about how to use that specifically in Unity. One of the core notes here is adaptive performance is currently only available on Samsung devices. While we do hold a very big market share and it's still very useful just for the difference it makes on Samsung devices, this is something we want to change, and we are pushing to have it enabled on more devices in the future. So let's take a look at what adaptive performance does. The first of these problems we mentioned is thermal throttling. So I'll give you an example. Let's say the target FPS is 60 frames per second at first, and as we can see at the start, 60 FPS is being rendered just fine. Soon, however, the FPS starts to shake and falls a bit sharply, resulting in an end FPS of 40. Obviously, that's not going very well. Why does that happen? Initially, a high CPU and GPU frequency is being used for performance, and the temperature of the device is increasing quite quickly. Thermal throttling is then beginning to occur, causing a pretty rapid performance degradation as the frequencies are really chunked down. At the end, the average FPS is about 50, but this sharp performance drop and inconsistent performance, especially towards the end of the experience, makes the entire game experience very bad for the end users. So how can you solve this problem? Let's say game developers know the timing of thermal throttling, as in they know exactly when thermal throttling is about to happen on their device. Something warns them, and then they can act accordingly and start preparing the application. They can start minimizing the amount of graphics it's going to use, or toning stuff down, or doing some of the other things we're going to make available. And that's exactly what the Galaxy GameSDK does. So it allows developers to know when thermal throttling is going to take place using the API we provided on high temp warning. This is essentially going to give you a value for the current warning level of the temperature. It's split into three main numbers. So warning level 0 is low terminal temperature or low device temperature. At this point, you're running fine. You don't need to worry about anything. Keep everything on high, basically. Warning level 1 means that the terminal's the device temperature has risen above a certain temperature and it's starting to get close to throttling. This is when you need to start thinking about toning stuff down. Thermal throttling is pretty imminent. And then finally, we have warning level 2. However, the return value 2 means that thermal throttling has occurred and your device is starting to slow down in order to maintain a usable temperature on the device. Therefore, through this API, developers can actually predict when the temperatures are going to be adjusted and prepare in advance to prevent the performance degradation we usually see. Also, we can provide a variety of temperature information, so we can provide a series of numbers. These are essentially temperature levels for a more accurate description of where the device is currently at. You can give a temperature level generally for the device, the CPU and GPU temperature levels individually, and also the skin temperature level, which is essentially how it feels for the user, or what the outer temperature is for the user that's holding it. All these information are provided as an abstracted level value. They go from 0 to 7 are the values we provide. And under this, it's still quite a general temperature information that's provided, but developers have a lot more control over it and a lot more knowledge of where the device is currently at. Developers can start to discern the temperature trend of the device, whether it's increasing over time, or whether it's okay. And then it's actually possible to predict the timing of heat regulation coming through when thermal throttling is going to take place. If you can see that the temperature levels are rapidly increasing, you know it's time to do something. Then we can use that information to prevent those sudden decreases in performance. The second half of the problem I described earlier was power control. So what can we do about power control? Now, again, I'll give you a pretty general scenario. So let's say the scene being rendered is quite simple. You're rendering quite a normal scene, maybe with not too much work going on. And yet you're still seeing quite a lot of heat generation happening that you maybe wouldn't have expected. Maybe the device has even started thermal throttling despite a very low workload. This is most often caused on mobile by using a high CPU or GPU frequency and therefore a high current, often when it's not actually necessary. On mobile, the frequencies tend to vary quite a lot, since the device doesn't really know what the upcoming workload will be, and it's not really programmed knowing that it's going to be a game that it's running. It could be running anything from a photo processing tool to a text tool or something. And as you know, using a low CPU and GPU frequency and therefore a lower current is always the most efficient if you can still maintain your performance at that level, and that minimizes heat generation and also power, battery consumption. Therefore, unnecessarily high CPU and GPU frequencies should be reduced in non-complex scenes. Generally, however, they don't have control over this. However, with the GameSDK, it is possible to actually control the max frequency or have some control over the max frequency of the CPU and GPU using the set level with scene API. This is an extremely high level of control for game developers, and it's actually extremely powerful in maintaining performance over long term for your application. So we actually give you the power to manage or suggest levels for the CPU and GPU individually. So you might be able to say, okay, in a scene with minimal GPU work, we can decide the CPU frequency needs to be set at 2, but the GPU only needs to be 1 because there's not a lot of GPU work going on. Therefore, in the situations just described, so I might have just described like a loading screen, a character selection scene, or just some more empty area of the game, you can save a lot of unnecessary power by controlling the CPU and GPU frequencies independently. So now we're able to actually adjust the CPU and GPU max frequency. However, in order to accurately control and use it, you'll need to be able to check whether the device is actually bottlenecked and where it's actually bottlenecked. So let's go back to a scenario where we have the CPU and GPU frequency set to 1. Suppose the target FPS is 30, but the actual game is running at around 20 FPS. In this situation, you need to decide whether you want to increase the CPU or the GPU. Now, you could certainly just put both up, but this is obviously not the most efficient answer, as in this case, as we discussed, you always want to be using the minimum CPU and GPU frequency combined as possible to maintain your target FPS, and if you're just putting them both up and then one of them is just wasting energy, then you're wasting quite a lot of heat there, you're wasting quite a lot of temperature gain. Therefore, we need to know which frequency to decrease, the CPU, as in the first value in this set level function, or the GPU, as in the second value. So in general, it's very difficult for the developers to know the exact bottleneck point. It's very difficult to tell how much work the CPU or GPU is doing without actively profiling it, without running it through a series of tools. So once again, what can the GameSDK do? The GameSDK has a bit of a solution to this one as well. So we have a very general bottleneck check, which tells you A, what's the general frame time, and B, what's the GPU frame time. So it can then provide a corresponding amount of a frame that basically the GPU is taking up. So in the scenario on screen here, let's say the whole frame is taking 20 milliseconds, the GPU is taking 16.23 milliseconds of that 20 milliseconds. That means 4/5 of the total individual frame time is being taken up by the GPU. I'd say that looks like a GPU is struggling scenario. It's definitely priority here needs to be given to the GPU. You could then use this information to say, okay, assign a higher level to the GPU, give it level 3 or something, level 3, and then on the CPU, give it a level 1. It doesn't need to do as much because there's obviously not as much work coming through. So that was a quick description of how to use the Galaxy Game SDK and some of the incredibly powerful tools it offers you in order to maximize performance and give you an actual control of the device. Using the Galaxy Game SDK, we can actually obtain real-time information from the device. We can obtain temperature information. We can obtain what the current situation of thermal control is. We can obtain actual values for the CPU and GPU frequencies, and we can also tell roughly what the current bottleneck is, whether it's the CPU or GPU. Now, using this information, we can actually pass that straight into the game engine or the game itself, and then the game can adjust performance and quality settings in advance to avoid the sudden performance degradation and maintain general maximum performance. This also means we can manage core frequencies and avoid heat gain at all times, which is extremely powerful. So that was Galaxy Game SDK. Now I'm going to explain how adaptive performance, which is the Unity implementation of Galaxy Game SDK, was applied to the actual Call of Duty mobile title that's released now in the wild, and I'm going to tell you what the result was. So I'm sure many of you are already familiar with the title, but I think we can just indulge and check it out all the same. So as you can see, Call of Duty is a very powerfully graphical game. It's a game that utilizes real-time lighting operations, real-time shadows, various graphics effects, post-processing, many animation operations, as well as networking and really fast gameplay. So as you can probably imagine, it's a very heavy game on mobile. Of course, many other optimizations were made for mobile in many ways to ensure maximum performance, but what did we add with adaptive performance to make this even better? So first of all, Call of Duty is a very fast-paced game. It supports fast live-action matches and much longer battle royale matches. In such a high-paced game where every moment really makes a difference, the last thing you want to do is lose due to a sudden drop in performance. For example, when an enemy rounds a corner, if you suddenly hit thermal throttling, then you're going to lose a lot of performance, you lose a lot of frames, and, well, it doesn't give you a very good advantage. So what did we add to prevent this? So adaptive performance is already active in Call of Duty. It's doing several things. The first of which is it's enabling something called the quality scale factors. So we added these as part of the general game. They modify the shadow distance, the foliage level of detail, the animation level of detail, and also, if necessary, the target frame rate. These are essentially the things in the game that get modified as the device starts to heat up, as the game SDK starts to notice that the device is heating up. In addition, we also have the power management policy or the power control policy. So this is pretty much exactly what I described earlier. The bottleneck detection logic I mentioned earlier is always active, so it's always trying to tell whether the CPU or the GPU is more busy, and then it's trying to up the CPU and GPU frequencies appropriately whenever it's required. So this allows it to maintain the minimum amount of frequency needed to hit the target FPS, but doesn't waste any unnecessary CPU or GPU spinning on the least busy core, and mitigates excessive heat generation while still maintaining the top performance. So all of these factors are modified dynamically during gameplay. The gradual performance maintenance was deemed worthy of a gradual, very small visual difference. So what's actually visual in the game as a difference due to adaptive performance is, first of all, in the top right GIF, you can see that the shadow distance is reduced gradually from 80 to 50. So this is a distance at which shadows are actually rendered for objects. So the default is 80. As the device starts to heat up, that gradually reduces down to 50. And realistically, the actual visual difference is not that huge. And the player is certainly not going to notice this after like 15 minutes of gameplay. When this is actually reduced all the way from 80 to 50, the maximum CPU effect was about 10% saving. This is a very significant saving in a CPU bottleneck situation, and actually makes a very big difference to the amount of power being used, the amount of heat being generated, in order to prevent that from hitting that thermal throttling point. The bottom right is also a visual difference for the foliage LED. This one goes down from 1.0 full LED to 0.8 or 4/5 LED. So this manages the level of detail of bushes and trees, and also controls the distance at which some of these are rendered. So it's basically an LED bias. It does cut a few objects out at very far ranges and make a very small difference to mid-range foliage level of detail. But to be honest, again, the visual difference is very small, and worth noting is this is probably a likely trade when a player has been playing for about 15-20 minutes and we're getting a saving of up to 5% on the GPU, which in a GPU-loaded situation is extremely important, makes a huge difference in how much power is being used. And yet, to clarify, these are only happening at quite significant periods into the playtime. So these players are only going to actually have to see this after 15-20 minutes, maybe even more of playtime, and then it's only going to happen when thermal throttling starts to take over. So in terms of an actual final FPS difference, over the same period of play, making just those minor changes, we saved an average of 4 FPS. So that's a 7% improvement from the normal conditions running the game and adaptive performance taking over and modifying some bits very slightly. It's a period of about 20 minutes of play in the Battle Royale mode. We also saved, on top of that, about 7% GPU usage just due to the quality scaling factor adjustment, so that's going to make a really big difference to power and when the device actually starts to hit thermal throttling, which is extremely important, again, in making sure that we maintain that 60 FPS or 58 FPS all time. So what was the actual temperature difference? Now we've seen how much FPS is saved, how much less hot are we getting the device. So the temperature device data here is on the left, blue is the adaptive performance situation, and orange is the default normal data of the game just running as usual. As you can see, the starting temperature is roughly the same, but as you play the game, you can see that the temperature is reduced quite significantly when adaptive performance is run. On average, this saves about 2 to 3 degrees. This value is primarily explained by the values in the max frequency table on the right. So in the normal situation, relatively high CPU frequency is allocated all the time. That's the orange line jumping up and down, which leads to really early heat control situations. Thermal throttling starts to take over very fast. And as you can see, the CPU frequencies and GPU frequencies are not really stable ever, and shake in the second half, especially as that's the point when thermal throttling has really started to take place. Notably, in the adaptive performance case, GPU is actually kept at a very stable line, so that's the green line on the graph. The GPU is kept very stable because adaptive performance notices that the GPU is really taking quite a hit. It's using quite a lot of the performance here is based on the GPU workload. So it actually assigns a higher GPU load in order to maintain the good performance, and then uses a very slightly lower, or considerably lower, CPU frequency in order to make sure that we actually make up that performance. And since the CPU isn't actually doing as much, and it's handling its workload very easily, we can save some power, which we can then invest basically back into the GPU in order to rebuild the performance again. So the key part here is that adaptive performance is focusing the device resources where they're most needed. So rather than wasting power upping the CPU frequency, it lowers the GPU, gives the GPU it lowers the CPU, it ups the GPU, gives the GPU the steady higher frequency it needs. Therefore, the performance is maximized while temperature increase is minimized. As a summary, both the Megacity demo and Call of Duty Mobile are both very good test cases with very good results for adaptive performance. This is notable really because in console games like on Xbox or PlayStation, quality scaling is extremely common. For each game, dynamic modifications are always being made to the game's quality to offload very significant amounts of CPU and GPU workload, often with very significant or not very significant visual differences. So this GIF above is actually showing a fairly drastic series of reductions in quality from 100% resolution to 50% resolution in Call of Duty. As you can see from the following table, making these modifications has a huge runtime saving and can save a lot of power and heat. In many cases, the final changes are very worth the visual loss to the end user. So it's likely that you're probably not going to go all the way down to 50%. That kind of resolution drop is maybe a bit too much. However, going part way over a series of time, so if we gradually moved it down to 80% resolution, let's say, as the device starts to heat up, we get a 10% saving in GPU, which makes a really big difference on the temperature long term, and does a really good job of making sure that the temperature is always below that thermal throttling point, or as close to it as we can get without going too far, significantly above it. So that was the general adaptive performance in action. I hope I've made pretty clear the benefits of using it. Before I finish, I did promise to mention some of the exciting updates that are coming to adaptive performance and Unity in 2020, and what we did with Bottleneck in order to actually test these out and see very quickly what the performance was. So one of the key features we included here is the adaptive performance scalers. So these are automatic scalers in Unity based on device temperature. They essentially modify default graphics options in Unity without the game developer actually really having to do anything. So they can, of course, be modified by the developers and are chosen by us to be as with the minimum intrusion, whatever the least intrusive we can have to the game as possible, while giving us a long-term graphic scaling here. So generally the graphic scaling is very small, it's very unintrusive, but giving us some very good performance improvements over time. The other feature I haven't mentioned here is called the simulator. It's going to allow developers to simulate the effect of adaptive performance scaling without actually having a Samsung device. So it's like a software emulated Samsung device to determine what the differences are actually going to do, how much they're actually going to change, and what sort of performance you're going to get, to allow the developers to see whether they're happy with the impact the changes are going to have without having to actually test on a Samsung device. This is another FPS graph. In this case, this is just the default adaptive performance 2.0 features to the test. So we just put adaptive performance 2.0 into the Bottleneck demo and turned it on, see what happened. And the results are pretty good. So we got a consistently higher average FPS. That's from 54.4 to 57, which is a really good performance improvement for making pretty much no physical changes. And in terms of CPU and GPU, again, we're getting a CPU saving in this time rather than a GPU saving. So we're cutting down the CPU and upping the GPU again to make up for work that we need to be done. And on top of that, we get a consistently lower temperature. So again, this is actually right from the start, we're getting consistently lower temperature and notably a lower CPU frequency, and again, more stable GPU frequency to make up for the higher GPU workload in this application. So the final big addition to adaptive performance in version 2.0 is VRR. That stands for variable refresh rate. This was primarily introduced in combination with the final series of Galaxy devices we've released recently. So these are the first series of Galaxy devices to support high-speed displays, which is 120 FPS on mobile, which is really insane. This allows users to determine which scenes of the game should use the high refresh rate and which to use on low refresh rate. So this is a pretty huge bonus that allows users to boost the refresh rate in more exciting areas of the game. So when they actually go into the application, for example, in the Temple Run style game you're seeing here, 120 FPS during the actual gameplay. But as soon as you pause or go back to a menu or have any other kind of cooldown period, you can cut it right back down. So you could have it at 96 FPS, 60 FPS, or 30 FPS in order to save power in between heavy periods of usage. The usage of this is visible in our adaptive performance variable refresh rate sample, which comes with the package when you download it in Unity. This is an all other adaptive performance samples are found just default by downloading the package, and they'll get them from the Unity package manager. On the subject of adaptive performance 2.0 samples, there are several other samples displaying much of what I've discussed already in this presentation. If you're curious about anything I've discussed in this session, feel free to visit those samples. They're available now in Unity just from the store. The thermal sample is going to display the temperature usage, how hot your device is getting. The bottleneck sample will show you how the automatic bottleneck detection logic looks in action. And finally, the automatic performance sample puts everything together and allows you to kind of watch the frequencies being dynamically updated as new bottlenecks are noted. So to make a final summary of what I said in the last approximately 30 minutes, adaptive performance does three major things. It monitors and reports your device's thermal condition. It ensures your device is running at the most efficient frequencies at all times to maintain performance. And it also dynamically adapts the game's performance, the game's content to maintain performance. Feel free to contact me at benjamin.m@samsung.com or the team at gamedev.samsung.com, or visit our website at developer.samsung.com/game. Other than that, thank you very much for attending this Unite Now session on adaptive performance. I hope it's been of interest to you, and I hope you've learned something new. There are plenty of other sessions available on the Unite Now website. That's unity.com/unite now. Thank you again, and enjoy the rest of the conference.